Swayam Prabha. Digital India. Educated India.
Nice to see you all, and yeah, it was nice seeing you as well in the seminar yesterday. We'll discuss some hydrogen today as well. I will expand a bit more on some of the things that we discussed yesterday. But before that, let me take it where we left it, and we'll also discuss a little bit fatigue as well. But before that, let me take it where we left it and go back to those carbon nanotube composites. So this was yesterday, and we didn't finish. We left it just about here. So we saw the fiber reinforced composites, and finally carbon nanotube composites. So this is the last item of application of phase field to composites. The motivation for us, at least, I mean, there's a lot of people working on carbon nanotube composites. These are sort of smart materials. Carbon nanotubes have some interesting properties. The motivation for us was to use them as sensors. So this was more a civil engineering type of application. So the idea is to do either embed those carbon nanotubes into concrete or create some composites that will act as some sort of smart skins. So there's an idea of monitoring structures for damage. This is often complicated and done at a global level, but often a lot of the problems that we have in structures are local, like corrosion and so on. So we want to put those skins somewhere where they tell us some sort of local damage has occurred. And the challenge from a scientific point of view is more that, you know, those nanotubes are very small, as the name suggests. They normally have a very large aspect ratio, and they're difficult to incorporate in the continuum, right? How do you handle those tiny nanometer tubes at the continuum level? So we used two approaches. The first one was to look into mean field homogenization to determine their effective mechanical properties. So this is what you see here. You have two homogenization steps, the double inclusion scheme and then the Mori-Tanaka scheme. And then we also included the fracture property. So this was a first step. This is a kind of a pre-processing step. You do this mean field homogenization. We have a Python script. You do this before you run your phase field simulation, so that gives you some effective mechanical properties. And then you run your phase field fracture analysis, where you also incorporate some sort of, you know, underlying behavior. So in this case, we wanted to capture the fracture of the carbon nanotubes, the carbon nanotube pull-out mechanism, and also this kind of agglomeration mechanisms. So you define your fracture energy as a function of, you know, the reference, the matrix one, plus this ones related to the aggregation and the pull-out and the fracture of the nanotubes. And we see that this was needed, this agglomeration step was needed, otherwise we wouldn't be able to capture what we see on the experiments. This is the fracture energy versus the carbon nanotube mass fraction. You can see that the carbon nanotube mass fraction has an impact on not only mechanical properties, but also fracture properties. So there's some sort of toughening effect related to the application of these nanotubes. So this is what the effective mechanical properties look like. So these are, again, all a pre-processing step. We're not running any, this is all, you know, analytical equations, mean field homogenization. If anyone is interested, you can find the details on the paper. But we're not running any sort of phase field simulation for the time being. We just, you know, for different volume fractions of carbon nanotubes, different aspect ratios, we're seeing how this changes the Young's modulus and fracture energy. And this, of course, certain aspect ratios will favor this fiber pull-out mechanism versus the fiber fracture mechanism. We then incorporate the phase field. You can see this is a classic example where you have a plate with a hole, and you see how the phase field, eventually the crack sees the hole, is attracted to the hole, and then eventually grows from the other side of the hole. And you get this kind of force versus displacement response that is depending on the fraction of carbon nanotubes. You can see that, you know, it's a linear behavior. Then you see the first drop in load associated with the growth of the crack into reaching this hole. But you still can retain some low carrying capacity. You haven't completely broken your component. So then you see then cracking initiating here. Again, the phase field can predict the nucleation of cracks. So we can see a new crack nucleating here, and then eventually the complete failure of the component. And you can see that, you know, the whole package can be captured without convergence issues. But of course, as I said, what we were motivated on was on capturing this sort of multi-physics, smart material type of behavior. So we wanted to develop a piezo-resistive electromechanical model. Here we need to account for both the degradation of the stiffness and electrical conductivity. And this is something that we discussed the other day. So I think actually there was a question about, you know, if you need to come up with your own degradation function, what you need to do. So this is the degradation function, normally called G, that we use for the phase field. So normally we use this quadratic form. Every degradation form that you need, it has to be, it has to be equal to 0 when the phase field is equal to 1. It has to be equal to 1 when the phase field is equal to 0, and then the derivative has to be equal to 0 when phase field is between 0 and 1. Oh, it has to be negative when phase field is between 0 and 1. So basically there's some conditions on your degradation function, but we initially decided, okay, why add extra parameters, right? We could use the same degradation function for the permeability as for the stiffness, for the electrical conductivity and for the stiffness. And we saw that this was not okay in the sense that we were not able to reproduce the experiments. We needed to change a little bit and do a much more, so this is the H1 is here. We needed to do a much more abrupt reduction in electrical conductivity in order to capture the experiments. So yeah, it's difficult to know exactly from first principles what's happening physically, but in order to fit the experiments, we had to do that. And you can see some examples here. This is a piezoresistive electromechanical modeling. So again, we're solving for an electric field in addition to the deformation in the phase field. And I'm not telling a lot of details about that now because I'm going to have a dedicated lecture on multiphysics phase field modeling. But the idea, you have a uniaxial tension test where you're applying an electric potential. You see here, you have no crack. Eventually, when the crack completely grows throughout the sample, you have a sharp discontinuity in the electric potential. And you can see here, this is the experiments, and this is the change in electroresistivity with the strain. So it seems to be in good agreement. Then we also tried other boundary value problems. So this is a plate with a crack that we rotated in the multiple directions and tried to see, again, the same trends, right? Basically, when you have a crack, you lose completely this conductivity. There's a discontinuity in the electric potential. And this is what we wanted to see because our application, our idea was to use this kind of piezoresistive smart skins that will tell us when a crack has grown and by changes in this electric potential. This is what the engineer will measure. And we can also do it in 2D, 3D. So this was a 3D example where you have multiple defects to start with. So it reminds me a little bit of the pipeline that we saw yesterday. So some defects to start with, you have an applied potential here, and you see how the electrical conductivity goes okay. But then eventually those defects merge with each other, and then you see the discontinuity in electric potential. That's basically the idea. This is something that is very much ongoing work, but this is the last part of the carbon nanotubes. So here what we did is a two-step process where first we do some mean field homogenization, and then based on the carbon nanotube dimensions, so the aspect ratio and their orientation and their volume fraction, we determine what are the elastic properties and the fracture properties. So it's a pre-processing step. Then with this homogenized model in the continuum, we run our finite elements with the phase field fracture and with electrical field on occasion. The idea was now, okay, is this mean field homogenization model perfect? It does work okay, but we can see that for certain conditions we're not able to capture what we see in the experiments. So we were hoping to do a model where we have an RBE, where we actually resolve those carbon nanotubes. So basically try to enrich that mean field homogenization scheme. So for that we have this, the carbon nanotubes in there. We wanted to account for two mechanisms. One is electron hopping, and whenever you put them together, this conductive networking mechanism. So I'm not going to spend too much time on this, but there are various ways in you can introduce those carbon nanotubes. You can see this is all periodic boundary conditions, the carbon nanotube that appears here, then appears on the other side, and so on. So it's an RBE with multiple of those carbon nanotubes, and Leonel, the student, has done quite a lot of work in coming up with a scheme that can do this rigorously. You can see how they look like in Abacus. So these are bar elements, if I remember well, embedded into your continuum solid RBE. You can see how they look like in the RBE. This is the displacement field. This is the electric potential. Again, running coupled models. Then this allows you to first we make sure that the size of the RBE is rigorous. So we check the electrical conductivity and we refine the RBE to make sure that you are getting some sort of convergence. This is also electrical conductivity with carbon nanotube refinement. Then we get the variation in electroresistance with strain, and again we keep refining until we see a converged solution. And the same for the RBE and for the carbon nanotube. So we just need to make sure that the RBE is big enough, basically. And this is eventually you get the same here. So this is the length of the RBE versus the length of the carbon nanotube. Again, eventually there's a lot of scatter at the beginning, but eventually you converge to something. I think that's the idea. So these are heavy calculations. But this is the most interesting thing. So this is the experimental data. So we had a micromechanical model that was not getting close enough. So we enriched the micromechanical model. We added this extra parameter. And now we can see that, first of all, the symbols are the experiments. This is changes in electrical conductivity versus volume fraction. There's typically a big change after reaching some percolation threshold. And you can see that the RBE model does a very good job in capturing the experiments. And based on the RBE model, we can enrich the micromechanical model. This is something that we discuss in a minute, but I'll show you first some other examples. So this is the micromechanical model and the RBE model. So we do different aspect ratios, so 50, 100, and 200. And you can see how we can play with the enrich the micromechanical model to capture the RBE model. And again, this is the experimental data, the RBE. Here we seem to be a bit farther away, but when we change the percentage of carbon nanotubes, then we seem to be getting closer. Okay, I think that was all with the carbon nanotubes. It was something that was left over from yesterday, but I wanted to go through it. I guess the idea is that